Okay. Hi, everybody. It's great to have you with us. And it's a great pleasure to have Andrei come back to give us the second part of his talk on inductive construction of elliptic stable envelopes. Thanks, Andrei.
Well, thank you so much. I'm really touched so many of you zoomed in into this discussion in the middle of summer. And I also want to thank thank you all for being here, and especially since it's part 2, I'm particularly surprised, and also I want to thank my wife Ina, because for when we scheduled this continuation for weeks, it momentarily escaped my memory that today is our 29th anniversary with Ina, but she very graciously agreed that I should give this talk, and so anyway. So this is, while it's called part 2, maybe I will not assume you guys studied the notes from or watched the video for part 1. So maybe I'll try to kind of explain what was happening there in some slightly different words. So so maybe this is some first part of the talk will be explaining what are we talking about, and so what is elliptic. So covariant elliptic homology. So what is it? So well, is a scheme in a good sense of the word. so this is what's the ordinary homology. So this is. So I'm going to explain this. So this is ordinary homology, or maybe ordinary covariant homology. Suppose I have a K, a compact group, and we will be mainly interested in connected groups. So this is maybe connected. And those compact connected groups, they all very nicely correspond to let me try to get this away. Didn't work so well. So this is two connected reductive groups. G. And we will mainly interested in the case when in fact abelian. So it's a torus and a torus. And so let it act on the topological space X. And so then to this data, one associates a contravariant functor which goes to denote maybe like that. Sorry. So this is, I will allow myself this liberty. I will forget the compact group and I write G. You should really think of the corresponding compact group. So this otherwise things get just too complicated. So this is that, and that is a supercommutative ring. And this is a ring. So this is with injects here. So this is over the covariant homology of a point, which is just you take. So this is a particularly nice ring, and so this is maybe I'll write going to talk about. So this is the, sorry. So this, apologize, the spec of that ring. Well, let's just, you take the Cartan subalgebra and you divide it modulo the Weyl group. So in particular, we take it, we will be mainly interested in the case when the group is abelian. So that's just the Lie algebra then of the, so this is Cartan subalgebra in the Lie algebra of G. And so this is something, if I take the spectrum of that, this will leave, so the spectrum of that, or spectrum of this ring, this will be some scheme or super scheme. We will be mainly interested in the situation when all the homology is even, so it's an ordinary commutative ring. So it's an ordinary commutative ring over this thing, and so some finite. And the contravariant means that if I have a map, so if I have a map, the morphisms in this category is a map of group goes to group, space goes to space, so that the action goes to action, and this is contravariant with that. And now in elliptic situation, we don't have a ring. We just go to spectrum, directly to the spectrum of the ring. So this is an elliptic situation. So this would be now a covariant functor. So maybe covariant to again, well, strictly speaking, super, but we're not interested in super. So we will not see that much. We will be mainly in the cases where all the homology is even. Super schemes, and they over. This is a scheme with a map to. This is a scheme with finite. This is a finite length object that sits over the elliptic homology, and so this would be our point. And what this thing is, you take, well, I mean, there's a general definition. So this has to do, generally speaking, this has to do with, we're not going to do this general definition. This has to do with G bundles over an elliptic curve. We'll not go there so much. We just take kind of the elliptic analog of this Lie algebra. Namely, you take the co-character lattice, co-character lattice of this group G, not the co-character, co-weight lattice. And then you, so this is like a lattice that stands for the replacement of a maximal torus, like a lattice version of a maximal torus. We tensor it with the elliptic curve. So this is an elliptic curve. And we mod it out by the Weyl group. Right? So, for instance, so for example, if I have a torus, T a torus, then if I want elliptic homology of a point, that is, you take the co-character lattice of the torus and you tensor with the elliptic curve. So you get, in other words, you get as many product of as many elliptic curves as you have the rank of the torus. If you have a two-dimensional torus, you're going to get e squared. And if G is GLN, then elliptic homology GLN of a point. Well, you take this kind of thing. So this we take e to the n, because it has torus of rank n, and we mod it out by the Weyl group. The Weyl group is a symmetric group in this case. And then so that would be the n symmetric power of the elliptic curve. So this is the set of n unordered points on an elliptic curve. This is a set of like n ordered points. This is a set of n unordered. And then so this would be saying so that this is the space scheme. So this is going to draw. So this is something like the elliptic. You should think of this as like elliptic homology or point, and over that sits something which is a finite length. Over that, so it's kind of finitely many copies of that stuff. So it's this scheme. And then most important examples of this thing is that if I look at the orbit. So what if X is an orbit in particular? So if X is an orbit of G, so if I take maybe elliptic homology. Well, now I'm gonna run into notational contradiction, since I've decided I'm gonna write well, let me write this. So that would be, and I take a here. So maybe there's a me go back to my notation, to the good notation, which I have a compact group, and I have an orbit means a compact group modulo some subgroup, which I maybe denote gamma subgroup. Then by the basic axioms of the theory, that is just the same as elliptic homology of gamma of that point, that subgroup. So this says the bigger, the smaller the orbit. So this is kind of the size of the orbit. So the smaller the orbit, the bigger it's elliptic homology. So this is when we take elliptic homology, you go from spaces to schemes, so that this property has kind of reciprocal relation on size. What was small becomes large. What was large becomes small. Right? So in particular, will be for every space X. I keep making this mistake. So for every space X, so this X is something. So this is my X. And we have always there's, if I have an orbit, which I maybe denote this is an orbit. And then there's always an equivalent map, which is just just the inclusion of that orbit. Means I have I have done that. This means this, since it's a covariant map, this should give me a map from, I take the elliptic homology. Maybe this orbit has the form K mod gamma, and so elliptic homology of gamma of a point, that's gonna go into elliptic homology of K of X. For instance, suppose my X is sphere P1, and then it has an action of U1, which kind of rotation action. And then it has the north pole and the south pole, maybe the 0 and infinity. So this is my P1 or CP1 or sphere S2 have this action. So this is U1. And so it's U1 equivariant homology. What's it going to look like? It has two fixed points. For every one of them, I'm going to get a copy of the elliptic curve. So maybe I'll draw them in some different colors. So if it has a red point, which is 0, it's a fixed point. for this, I'm going to get like a copy of the elliptic curve. So this is E itself. And then I have another point, which maybe I'll draw green. So there will be another copy of E. And then I also have orbits. And in fact, I have a segment worth of this orbit, but it's homotopical is the same as one orbit. So it's this orbit, it's a free orbit. So this one is free. So its stabilizer is trivial, and so this would be its elliptic homology would be just a point, and so this is that. This is that intersection point. So this is elliptic homology of that looks like a union of two elliptic curve joined at a point. And more generally, you have any space X, I can reconstruct. So space X, I can write, can be written as a cell complex with cells of the formula disk of some size. So this disk cross maybe I'll write K mod gamma, and then correspondingly this would be this if I take the structure sheaf. If I take, so here the the way the space is constructed, I have my structure sheaf of the elliptic homology, which there is what does it look like? So if I have two free orbits, so I have two structure sheets of elliptic curve, and then they glued at a point. So maybe I'll write 2 OE plus another OE. Functions on one, functions on the other. There is a map that takes the value at the point. So this is goes to O of that point. And then the kernel of that are the functions on my elliptic homology of P1. So this is in this sense, my elliptic homology is built out of pieces corresponding to a cell decomposition. Here, cell decomposition here being a free orbit cross D1, and then two cells of the form trivial point. And so this would be there's an analog of this kind of thing. So there's some complex in which your your functions on elliptic homology sit. So this is the set built in pieces out of that. And that I stress the fact that what is big becomes small, what is small becomes big. So that's this. So this is one approach. And then another way to think about it. So this is another thing I want to stress is that what are the Chern classes? Chern classes, if I have a vector bundle over X, so this is my X. So I have my X. And if I have a vector bundle over it, I call it vector B. Right? So having a vector bundle over X, well, it's the same as to have a map from X to a point mod, so maybe vector bundle of rank R. Point mod GLR. Right, for QR, sorry, I keep confusing compact groups with reductive groups. So it depends if you just so, and then this means I should have a map from whatever group, whatever have a G equivalent vector bundle. So maybe there was some group action, whatever some group G acting on my vector bundle V, right? And so then I should have a map, and I do have a map from G X going to now. So this is elliptic homology of a quotient. Well, it's a quotient stack. This means GLR equivalent homology of a point. We decided that it's just R's symmetric power of elliptic curve. And that map, so this map is, those are the Chern roots. Elliptic Chern roots. Okay. And so then in particular, if I have now an inclusion of an orbit, so suppose I have some orbit. Sorry, I'm already used. Suppose I have an inclusion of an orbit, which is K mod gamma includes into X. Then when I pull back, so I can ask what would be the composed map. So what would be the composed map from elliptic homology of gamma or point? So this is going to go here. And what's it going to be? Well, this would be saying this records. So records this composed map. This records the representation of gamma in the fiber of V. Right, so this is, so I have a gamma is a stabilizer here. Gamma going to fix a point. And so this therefore will act in the fiber. Gamma will act in the fiber by some representation. This representation, this is recorded by, so this is like, for example, if I have a torus, that the torus would, I will just record the eigenvalue. So for instance, the example we considered in part one is that what is the elliptic homology? Suppose my X is the Hilbert scheme C2 endpoints with the action of a two-dimensional torus, which maybe I'll denote T1, T2, it's a set of diagonal matrices. And it's well known that cohomology is generated by the Chern class of the tautological bundle. So if I take so a point here, this is a set of ideals in the ring of polynomials with two variables. So whatever. So I C cross x1 xn, and so then you have of then you have a bundle which is the whole ring modulo that ideal. This is a tautological bundle of rank n, and then the Chern. What would be the Chern? What would be the Chern? What would be the Chern class as well? Here I have n unordered points. So maybe I'll take them. So this is some kind of coordinates. It's kind of x1, maybe not x. Maybe call them s1 through sn. S1. So S n of e. So here coordinates are. So here's a is a point with coordinates x1 through xn, or sorry, I wanted s1 through sn. And then my base is the sort of T1, T2, which I think of as T1, T2 as being the corresponding stands in for the coordinates on the elliptic curve. And then if I look at the so then my each fixed point will be a copy of that, where the set of this Si, that is the set formed by what's the fiber of this? The fiber of this bundle over some fixed point, which is a partition. That fixed point will look like. This would be the way it would be 1. One T1 inverse, T2 inverse, T1 minus 2, and so forth. Right? So this is a copy. This would be a copy. My scheme is a copy of however many partitions. So this is P of n many copies of E2 in each union of them, and they sit inside of E2, my base E2, and the coordinate along the Chern roots are the symmetric polynomials in S1 through Sn, and then the condition is that this up to this collection Si is this collection. That clear? Any questions about what this looks like?
What is P of n?
Oh, number of partitions. This is number of partitions of n.
So if I can ask again, just to.
So this is the same as the rank of cohomology of the Hilbert scheme.
Just so I understand what's going on, you're describing the elliptic cohomology of X by using this map to the Chern roots of the tautological bundle. Is that right? That's right.
So this is in general, those are just some functions, but for some varieties they're known to be actually coordinates. So if your cohomology happens to be generated by so in general cohomology, if you have a bundle, your cohomology maps to something like this. But if this bundle actually generates, if the Chern class of this bundle generates your cohomology, that map is an embedding. And that clear?
Thanks. Yeah.
All right. So so good. So this is at least maybe to recap, this was supposed to be the answer to question 1, which is what is elliptic homology? Now the question of number 2 is what is a elliptic homology class? So an elliptic homology class is so previously, so maybe I'll say a few words before completing the sentence. So previously, cohomology classes were functions on the spectrum of cohomology. So it was unambiguous. Now we have a scheme, and so of course we can ask for global functions, but we look at the scheme, which is like a union of elliptic curves. That's not going to have, it's the projective scheme. It's not going to have any functions. So the second best is a section of a line bundle. on that makes sense. So if in absence of functions, we turn to line bundles, which makes sense. And so where we're going to get line bundles? So in principle, peak of that scheme is an interesting thing. One can study peak of that object, and it's a kind of interesting thing to study in algebraic geometry or topology. But we're going to be content with something which is again with some tautological construction. So where we're going to get line bundles? So recall for every vector bundle, for any vector bundle V on X, we get of rank R, we get a map from elliptic homology of Gx to SR of E. And then what we can do is we can pull line bundles from there, pull line bundles back from there. And this has interesting line bundles. So one kind of line bundles for divisors, the same divisor. One such is when it's maybe I'll write it here. We have kind of like a theta divisor. It is a theta divisor if you think of this as some set of GLR bundles on the elliptic curve. But so that's a divisor where so coordinates here are what we're writing. The coordinates here are like S1 through SR, and theta is the divisor where one of the SI equals let me read what Konstantin says. Okay. Well, in the absence of untwisted, right? So then it's the only one untwisted. So let me. So one of the SI is equal to 0. That's a good. I mean, in more conventional terms, this is if I write it, if I think of a divisor where SI equals 0, this is the divisor kind of in more conventional terms like theta of SI equals 0. So this is more or less, as you can say, well, this is the divisor of like a product of the theta functions. So theta function would be a function. You can choose a particular one, but it's you may want to choose a particular one, but it's a function with one and only 0, and it's at the origin of the elliptic curve. So it's like a product, the divisor of products of this SI. Okay, so that makes sense. And now you notice that this is in fact, so this gives you a map from gives a kind of a map from V. It's clear that if you pull it back here, pull back, you're gonna get a class which we denote theta of V. This is a line bundle. And it's clear so that theta of V1 plus V2, well, it's just a product. Maybe I'll drag O times here. Just in would be, that would be saying like a section of that is a product of theta functions in the Chern roots of that bundle. And if I have two direct sum of two, then the Chern roots are union. And if I take, I get a product of two things. It's clear. And so it really extends, so it gives a map. From equivariant K theory of X to peak of elliptic homology. That clear? And that map, this you can compute from the line bundle what is the so this is like if I restrict it to, for example, I've restricted to a fixed point or restricted to another orbit, I'm going to get a line bundle in roughly the Abelian variety, and I can compute what would be the degree of that line bundle and what would be its image in peak zero of that Abelian variety. So this has, in other words, this has degree, also has peak zero. This can be really important for us. Means that you can construct bundles that are not only that are topologically trivial but algebraically not. So that's, or they're algebraically equivalent to zero, but they're not equal to zero. And what would be the simplest example? So this is one kind of simplest example of this construction. Suppose I have a line bundle. Suppose L is a line bundle, so it's already in peak G of X. And then take the group G, maybe take another copy. Another U1 or C star, or whatever, let's call it C star, which has nothing to do with anything we considered before. So maybe it has coordinate Z, just some other copy. And then consider theta of the following representation. I take L minus 1 times Z minus 1. Right? So this is a line bundle. Over what? Over elliptic homology of X, which I had before. G covariant homology of X. Cross this elliptic homology of that C star, which is, well, it didn't act on anything, so just might as well point over X or whatever. So this would be. Okay. In other words, right? So I can add a new group and I can make it act in this funny way. And what would be this like? So this is in conventional terms, a section of that. What does it look like? It looks like this has Chern root S or L, or let's call it S. This would have a section which is like theta of S times Z over theta of S times theta of Z. And so this is, in fact, this is like a section of Poincare line bundle. Section, this is like, it looks like Poincare line bundle. So my convention here that so this is theta is depends on an element in K theory, and so under the argument I use the operations in K theory. So this is a product in K theory, and this is a sum. So this is operation in K theory. So the K theory is the ring has product in K. Has product, has addition. So this would be. So if I expand this out, I'll have L times Z minus L minus Z, and then one doesn't matter, one's a trivial object. And so then I take its corresponding Chern roots will look like that. Right, so this says that this is once I have, so in other words, means the conclusion that we have plenty of line bundles. The conclusion of that, there's plenty. So if I consider elliptic homology over and this is, so sorry, I didn't finish this. So in particular, it has degree 0. Degree 0 in each variable. It's algebraically equivalent to 0 in each variable, because clearly if I set Z to 1, I get 0, and I get S to 1, I get 0. And so there's a value for each parameter that gives a trivial guy on the other side, but it's not trivial. And so that means that over elliptic homology, G current elliptic homology of X cross, I can add a new factor, which will be like the analog of that. I take pick G current pick of X, and then I take odd times of that with where is that, with E. So this is the analog of that. Over that lives some kind of universal. Well, maybe not universal in the sense that pick 0 of that might strictly speaking be bigger. We don't know. Lives is U, which is kind of like it's universal such line bundle. No degree 0.
Can you say one more time what the purpose of that auxiliary C star was?
We need I'm trying to say that this not only have interesting line bundles of degree 0, but in fact they naturally form families. And so we want something like some parameter space which would parameterize this line bundles of degree 0. And as such parameter space, one could, for example, naturally choose for every other line bundle, we can just scale. I mean, you can say, well, that's a group that just scales the fibers of that line bundle. That would be like, what would be this? What's this expression was expanded out? It says it's the line bundle. It's the line bundle as it was before. So maybe I'll expand it out. This would be like L times Z minus L minus Z, and then there's +1, which never mind, it's a trivial bundle. So this was our line bundle as it was before. This is our line bundle now with the additional action of its automorphisms, and there's just pure action on the trivial bundle, and that's just trivial bundle. That makes sense?
Okay, so it's scaling. It's like scaling the.
It's like scaling that line bundle, yeah. But it does really, if you when you trace it out, it gives you a family of line bonds. So not only we have interesting of degree 0 long, so they all along this. Okay. And so, whenever we want to say, whenever our strategy would be that we want the classes that we want. Elliptic homology classes. Which want will be sections of whatever, we wanted some kind of line bundle, whatever, we don't know, some line bundle L, tensor that U. We're not going to ask for something happening for one specific line bundle, but we would like to move that line bundle in all line bundles algebraical equivalent to that. At least we want a tensor with that universal, with that U. That makes sense? And the reason for this, we can ask, what would be the purpose of that? The purpose of that is that this has to do, so this variables here, these are the Kähler variables. In the image of contest. So I don't have time to go into this in some great detail, but this is the main applications here concerns solving some enumerative problems. And enumerative problem, one count curves into X and some one way or the other. And this counts record what was the degree of the curve. And this record is some generating function over all possible degrees. And so it's a function on this what people call the Kähler torus. As you take so in enumerative context, you take something like pick. So the Kähler torus there is something like that. You take this instead of being elliptic curve, you maybe take C star or something like that. And so then this would be very close relative to that, and this is how you solve some, you want to say, quantum problems in terms of just purely classical computation. Saying something, you're going to say something in terms of like a monodrome of some curve counts in terms of essentially purely classical computation. But that purely classical computation involves all these degrees of freedom, and it's kind of important that it involves them all. Like I said, it could, in principle, if we knew more, if we knew what was the whole pick 0, we could just throw that in too. But it's at least it's this. At least it's this much. That makes sense. Questions about part 2? So okay, to recapitulate, we said elliptic homology is a scheme. Elliptic homology class is a section of a line bundle. And then which line bundle? So this line bundle would be, one has to specify its degree. But once it specifies degree, then in principle, it's a good idea to vary that line bundle within all line bundles of a given degree. That is, vary them multiplied by anything that is algebraically equivalent to 0. But we may not know what's the, I don't know in general what's the whole pick 0, but at least it's this much. And that's enough for our purposes. That makes sense? So okay, well now part 3 is that what's the envelope? So question mark. So this is I recall. So maybe I recall the picture. Maybe you've probably seen it before. Certainly, if you look at my first installment of this course, there's some x, and then there's a fixed locus for the action of some torus, and then this fixed locus has some attracting directions. And some repelling directions. And these attracting directions, if we close them up, they can hit some different component of the fixed locus. Right, so we could hit some. They could hit some different component of the fixed locus. So maybe I'll write this as a F1 and F2. And so so this X contains a fixed locus of some torus, which in turn is a union of phi components. And we would like to assign a meaningful cohomology class to this attracting manifold, like for instance, right? So we want to continue on extent. So the question is to extend this attracting manifold, which is, so this is attracting manifold to the some subset in X cross, or maybe I'll write it out this definition. Attracting manifold to the set of pairs of some point X and some fixed point F, such that of pairs X and F, such that the limit A goes to 0 in some specified way, A times X equals F, and that's a submanifold inside X cross fixed locus to a canonical. Well, canonical, this will come automatically to cohomology class, elliptic class. And this sort of problems when you have a cohomology class given to you on an open, and you'd like to extend it to something on the whole space. It's actually very close. So this is, I hope Konstantin's like that. This falls into a general category somehow, more general category of questions, more general. More general category of questions. Like you have a semi-stable locus, it's an open inside. Inside, there's some notion of semi-stability or stability, and then there's a semi-stable locus, some open thing inside some X, and you have a cohomology class such, and here's the attracting manifold, and you'd like to extend it in some nice way to the cohomology class on the whole thing. And Konstantin did a lot of really important work on that, and then it to be continued by the NHL and a lot of people. So that's so this is kind of a very well studied problem. And now I'm going to say that this is in elliptic homology. What does it really mean? It means I have so typically what happens here. So if I have maybe call it. So here I have maybe my open, in this example, I have an open set U, which is X, and we take away the attracting manifolds take away the union. So bad notation. So maybe call already so many U's, so and conflicts with the union. So maybe I'll just write the word open. This open would take the union of attracting manifolds of all components which are kind of below, phi below our given component F1 in the attracting order. So if we take that thing out, then we have this is a nice open set on which we have the attracting manifold, and we would like to extend the homology class given to that by that smooth manifold. We would like to extend it to the whole thing. And what would this look like? So if I have I can so this is this would be saying so I claim that this is like, so for if you ask for sections to extend sections, this means an interpolation problem for sections of our line bundle L, whatever tensor U. And so how does this work? So if I have maybe I draw another diagram. So so this is my, so maybe this would be my this is my fixed locus F, F1, and then it has some attracting guy, and then there's maybe some other component F2, and then this, and then that's my whole X. Sorry. Somehow today I'm keep getting. So this is my whole X, and I'd like to remove some neighborhood of that F2 and what was below it. So so this would be my open set. Let me try a different color here. This is this open, or you can take it close if you want. Doesn't really matter. And so what would look the long exact sequence in cohomology? What would it look like? So if I have cohomology of my whole X, so maybe let's just have some. Sorry, let's have a. I apologize. Let me have slightly different notations. So let me denote. Let this part be X2, and then this part would be X1 with, so suppose my not supposed to, let the all the fixed components be ordered, and then I denote by Xi to be the union of neighborhoods, and this is a union of neighborhoods, of OI less bigger, sorry, J bigger than I of neighborhood of attracting manifolds of this Fj. So this X1 is this is all X1, this is X2, and then there's my X, which is something like that. And so then if I for example, if I look at the, if I want to see, look at x minus x2, so then the homology of that, so this would be, I'll just, so maybe let's abbreviate. So we have, well, maybe not abbreviate. Let's look at the homology of x minus x2. And in elliptic homology is some graded sheaf that lives on Y. So this is the grading. Grading in cohomology. Of the elliptic homology of x minus x2. I can restrict it to the open set, which is x minus x1. So this would go, this restriction. Open set, which is of x minus x1. And then so this is, and then the kernel. So this so this is, I'm saying take everything but the green and restrict it to maybe, yeah, you know, with the color coding. This is just that, and this is the blue, and this restricts that. And the kernel of that, well, this is the cohomology of some tubular neighborhood here. So it's some Tom space here. So it's like already some kind of Tom shift of the normal bundle. So this attracting manifold of F1. And this will be a long exact sequence of cohomology. So all graded. So this is what it looks like. And now the question of extending a cohomology class is a lift. It's a lift there. So we want a section. We have a section defined here. We have a class defined here. So here we have defined, and here we'd like to lift it. That's clear. And this is what this really what this is like. This is like I have a section defined on maybe it will help if we do an example. But before we do an example, I'll explain the general principle. So that is extending a cohomology class here is the same as inverting the restriction for section of line bundles. Right, so we have a map of a line bundle, we restrict it to some subset, and we'd like to invert that. The inversion of restriction of function, that's interpolation. And the key to solving that problem is by the long exact sequence, you'd like to know that the cohomology, you'd like the cohomology here to vanish. Like this. So if we take it, so we take this long exact sequence. Let me copy it. Copy. So now if we take it, now if we tensor it with, so we have some line bundle which maybe denote S, which is some fixed line bundle. We call it L, and then we tensor it with U. And so then we tensor it with S everywhere. And so this is the the lifting of a section or interpolation, this is controlled by the vanishing of cohomology of this shape. And that's what this is. Would like to cohomology here. And that is can be proven. And it can be seen. But let's do an example. Sorry, this may be a little too abstract, but let's do an example. So example. Suppose X is, I don't know, C2. And then, well, since we're talking about attracting reflecting manifold, let's suppose we have a group action on that C2, and then maybe it attracts with some weight, whatever, some positive weight, and then it repels this. So this would be attracting direction, repelling direction. Let's the repelling direction have the weight A minus 3 for something, right? And so then this is attracting. And so then also we can have some different group actions. So maybe we can denote that different group action, maybe call it B. Other elements. Other group action. We want to study things like covariance with respect to whatever automorphism, so I might have some other automorphism called B. Now, and this is my attracting manifold, maybe call this my X, and this is my X1. Oh, sorry, X sub 1. Right? So what is the elliptic homology of X? Elliptic homology of X. Well, X contracts to a point. So sorry, elliptic G, whatever my recurrent homology. Recurrent homology of X. Well, that's the same. X is C2 contracts to a point, so this is the same as a current elliptic homology of a point. And so this would be, if I'm working with tori, this will be just a bunch of copies of elliptic curve. One, another one. So this is for the variable A, this is for the variable B, and whatever other things I could have. Okay. And then what would be the elliptic homology? Current elliptic homology of X, and I take away X1. Well, now this now contracts to elliptic current elliptic homology of well, the horizontal direction I can still contract. The vertical direction becomes C star, and these are orbits. These are precisely orbits with the stabilizer. So here the stabilizer is the one-dimensional orbits of my group, and the stabilizer is the kernel of this character A minus 3 equals B. Right? So the stabilizer, so if I have my elliptic, maybe let's assume we have only two variables. So this would be this is like one elliptic curve, another elliptic curve with coordinates. What would you like? Maybe call this coordinate B and this coordinate A. So this is, and now in here, the kernel of A minus cube B, well, that's the image of B equals A cubed. So this looks like this. Right? And so then the question is, if I have some line bundle, S here on this, and I'd like to restrict it to restrict to just that. Restrict to that curve. Right? So then the question: when can I interpolate a section of a line bundle from its values on the curve? That makes sense. And then, moreover, in this variable b, we were b is some parameter in which in that variable b is like a k, I don't know, some parameter b. In this variable, such as definition, in the variable which are not, we're interested in some group action, which is this a, and in all other variables, in all other group elements, we allow poles. And so it's a question if when can we interpolate a section of a line bundle where can we interpolate a section of a line bundle in 3 points on the elliptic curve? Right, so since we allow poles in B, might as well assume we visit at a point in B, and so then it's a question in that variable. If I have a line bundle of some degree in the elliptic curve, where can I interpolate in 3 points? Well, if it's a line bundle of degree 3, then in general I can interpolate. So if I have a question, so if I have some line bundle, if S is of degree 3, which stands to reason because we would like S to be like the attracting manifold, and so it better have this degree 3 here. This is the degree. This is the same as degree of attracting manifold. Degree, if I look at the attracting manifold, the class of the attracting manifold is a section of some line bundle. So this would be, this attracting manifold is like this theta of A minus 3B. So then we, and it's generic, then we can interpolate, it's uniquely interpolate in 3 points. So this is, if I take, so if I take, in other words, an elliptic curve, I have a line bundle, and then I take one of its values at 3 points, and then here will be L turned out minus by 3 points. Then the cohomology, the all cohomology of L minus 3 points, that is typically 0 unless this bundle is trivial. Unless it's trivial. Maybe. Sorry, I was saying something very basic. Suppose I have a line bundle of some degree on the elliptic curve, degree D. Then by Riemann-Roch, it will have D sections. And I'd like this D section to have specific values at D given point. So I can always achieve it generically. Namely, if I take D given points on the elliptic curve, I take restriction to this D point, then the kernel of that will be my line bundle twisted down by D point. So we'll have degree 0. And if I have a non-trivial line bundle of degree 0 on the elliptic curve, or general abelian variety, all cohomology of that line bundle is 0. And so in particular, that says that the cohomology, so maybe I'll write an exact sequence in a way. So L restricted to 3 points. And if all cohomology of this are 0, that this map is an isomorphism. That makes sense. And if I have a family of line bundles, then what can happen in the family of line bundles? in a family of line bundles, if it's a non-trivial family, then at worst that can happen is the first cohomology can jump on the divisor. In general, if I have like a d-dimensional family, really d-dimensional family of line bundles, the d cohomology will vanish. So if I have the first cohomology will appear will be d cohomology. But if I have a non-trivial family of line bundles, which I know is non-trivial because I constructed it, this is why I introduced all the scalar variables. In that family, H0 will never appear, so this will always interpolation always has a unique solution, and it has a pole. So when this bundle is trivial, this means I have a pole. Means I have my interpolation problem pole in this variable. Well, in this case, it is this pole. I have an interpolation problem. This is, well, maybe let's do an example with 1 point. That makes sense. So suppose I have a degree 1. So if I want to know, if I want to know something like this, and if I want my oh well, you can do an example with 1 point. That's sorry, I have to somehow wrap up this discussion. Maybe we maybe I'll summarize this discussion, and then you can see if you have questions. So to extend an elliptic, so elliptic homology class is a section of a line bundle. To extend an elliptic homology class from an open to a larger open, that's an interpolation problem. It's an extend a section of a line bundle for, in fact, a closed subscheme to a larger subscheme. And solutions of interpolation problem are controlled by some cohomology group. And that cohomology group can be shown to be trivial on abstract grounds of the kind that if I have a non-trivial family of line bundles in the abelian variety, this will have no H0 and will have H1 only jumping at divisors. And so this extension, if I study it as a over my parameter space, there will be some points, some bad divisors, some resonant divisors on which they'll have poles, and then everywhere else will be unique solution. That makes sense?
How did you decide to allow poles in the B variable?
Well, because so we fixed some group, and then in addition to that group, we can have some commuting action. We can have the Z variables, and then in principle they all play a role. What we're going to use the fact is that as we vary the Z variables, my line bundles really do change. That's very important. So this is really a non-trivial family of line bundles. And so in particular, in that whole thing, I have some commuting variables, this variable, the scalar variables. In them, in principle, there are loci where that line bundle in question could be trivial, and then I will have a pole. So if I decide there will be no, this will be sort of, this is, in fact, so maybe we will get to examples that will be maybe a little more clear. That those poles there for good reason.
So the significance of the elliptic curve instead of just usual cohomology is that it's compact. That's what buys you this uniqueness at the end.
It's usual cohomology. You can phrase there's some stuff you can say in K theory, but the kind of thing that we want like very strong vanishing for cohomologies of line bundles for a current cohomology of a point. So if I'd like So if I take ordinary cohomology or K-theory, you're gonna get a fine algebraic varieties, and so they'll be kind of the opposite to cohomology vanishing.
Yeah, right. Because elliptic curve is how to say proper, and then
Exactly. Yeah. So we want some
Yeah,
cohomology vanishing. Yeah. You can phrase. So in fact, in between the first installment of this talk and the second installment of the talk, I've put some kind of partial notes on the web, and you can. There's some discussion of a limit to K theory, what's the required cohomology vanishing, and so forth. But it can be said. But what is really easy here is this. So maybe so. So maybe so this is for Konstantin maybe. So in your business and Dan's business, the key is that you want to pick some like a polynomial with a Newton polygon that fits certain profile, and that would be said that can be here's rephrased is that somehow since we want to move the ability of move that Newton polygon is the analog of that here is the ability to just take a line bundle and twist it by degree zero line bundle. And the fact that there's this kind of so this is if you work say in equivalent K theory, maybe the direct analog of that is if you work with one-dimensional torus is that's kind of a trivial cohomology vanishing. It's like saying of a polynomial of some degree on a torus is determined by so many points. That's not very interesting. But if you work with multidimensional tori, then it kind of becomes an interesting cohomology vanishing statement. But for elliptic curve, that's all trivial. It's just if I have a line bundle in elliptic curve, which is degree zero, this is to say algebra equivalent to zero, then all of its cohomology are zero except when it's trivial. So that's really the statement, and that's what buys this interpolation problem more or less automatically. All right. So maybe we'll decide that I somehow tried to explain, and like I said, there's some sources. If in the unlikely event that you might be interested in learning more about it, I've continued to give these lectures on Wednesday, and there are recordings on the web, and you can also, I don't know if you can read part one of this paper, and that's the elliptic homology part there is pretty brief. So like I said, the cohomology vanishing is very, very direct. And so applications. So so first of all, this kind of gives this well, first of all, it gives construction of elliptic. Maybe zero is good. Give construction outside of the particular. So with outside of cases, construction and more general. So with Mina, we construct the elliptic stable envelopes by some global considerations, which is fine because they also give formulas and stuff. But it's strictly if you want an actual proof of existence, that this kind of inductive argument is nicer. And so then this could be applied, and so this would be applied to maybe like the monodrome problems.
In which generality does this give you a construction now?
You need something like connected reductive group acting on some variety with maybe polarization and maybe like not strictly semi-stable points or something like that.
So very little.
Yeah, very little. Yeah. So this is so they so exactly more or less in the setting which is actually congruent to the setting. Well, at least as large as the setting considered by Konstantin and Dan in this in their work. So monodrome problem. So what will be the monodrome problem? We already studied. So we have so we study when one counts. This is I tried to explain it last time, so maybe I'll try to be brief. Assume that you have so so maybe we can study like a vertex function. This is a sum over all degrees. Then z to the d. So this is a variable. This is really a variable in this scalar torus. So I pick gx 1 times c star, that scalar torus, and then you take the count, maybe you kind of evaluation count quasimap. So evaluation push forward, or from which space to which space. So space are take quasimaps from P1 to X mod G of degree D, and also the non-singular at infinity. And so this evaluation map is the evaluation at infinity, push forward. And then additionally, there is an action of C star of Q, variable Q that rotates the domain, Q in C star, automorphisms of the domain of my map. And there could be some commuting action, whatever commutes with my group can act here, some group of automorphism can act there. Some other group can act there commuting. And then what you push forward is some symmetrized virtual structure sheaf. And so where does this live? This live in you take this equivalent G automorphism cross that C star equivalent K theory of X mod G. You have to localize it because this is a slightly non-proper push forward. And then you take formal power series in Z. This is also known under many different names. This is also the I function. This is also the disk. What would you say? What would you call disk amplitude, disk whatever, disk something, disk partition function. Anyway, some well-known objects in the world. Many people study it. And what this is some series. That series is some kind of very fancy brother of the Q hypergeometric function. In particular, satisfies the Q difference equation. equations in the variable z, and also in the variables in the kind of, you can have a, maybe call it, I don't know, torus A inside the group of automorphisms. Just something like that. Of course, you can, if you write it out, this looks pretty scary. This looks like some kind of, you know, for the Hilbert scheme, that's going to look like this one-leg PT partition function. So this is some complicated object, but it does solve a Q-difference equation. And so then the basic question for this is the monodromy of that. So the monodromy. So the monodromy of a solution of Q-difference equation, if what is it, the monodromy solution of Q-difference equation? It's solution of a Q-difference equation is written at is written about a point where fixed by Q. So it's either the variable is 0 or infinity. So so here it's a series around 0, and then you can compare some monodromy. This comparison of solutions between, so it's like a fundamental solution. So an example of monodromy is like a fundamental solution. Maybe call it phi written at maybe z equals 0, and composed with phi inverse written at some other point, maybe z equals infinity in some sense, something like that. And so this object clearly, so this is since they both solve the same Q-difference equation, this would be a periodic.
Of the equation, Andrei, so those phi's are matrices, right?
What?
The phi's the matrices of.
It's a matrix, a fundamental solution, yeah. And this is periodic in Z, Q periodic in Z, right? I mean, here I assume that, so these equations in very broad generality can be shown to be regular difference equation, not always, but I already said I assume that X has a polarization, means it's already kind of balanced. Its tangent bundle is a sum of a bundle. Polarization means you have a bundle such that this bundle plus the dual is equal to the tangent bundle in K theory. So this is like a symplectic type of symplectic condition. So that's under hypothesis like this, you can prove that this in fact equation is regular. So you can study it not only at z equals 0, but also at z equals infinity, and then you can compare it. So this is satisfies importantly somehow regular. It's kind of an important thing here, but so and so this is with in this paper with Mina, we already studied in this variable A, we already solved that problem. This is in this paper with Mina. Here we studied that problem here, and the answer there is you take, well, this is for, we studied for Nakajima quiver varieties, already very, very broad quiver varieties. And the answer there, it's like it's the R matrix, meaning the R matrix you vary for A, you change the role of attracting and repelling directions, and so you compare stable envelope. You take a stable envelope with some correspondence. You take that correspondence with one choice of attracting directions, and with another you take the ratio, and that is the That's the monodrome. And similarly here, you can show that, well, I'm not going to list maybe all hypotheses since I want to get somewhere. But so here in the scalar variables, you can do the same thing. So we take this elliptic G-crank homology of X, right? And then there's a map here from, so if I take quasi maps, they go to, this is with some choice of stability condition here. So there's, you can take the stable. We assume there's no strictly semi-stable point, and maybe one choice, stable plus, and then there's another. So this is the analog of z equals 0, z equals infinity, and there is another choice, stable minus. And then, so the stable envelope here is to extend sections of a line bundle from, so this is in fact an inclusion of a closed set, and the stable envelope is interpolation problem, is extension of sections of a line bundle from some line bundle here. You have sections. Well, in fact, sections of the line bundle you need is like the theta function, theta bundle of a polarization of X. Tensor that U, and so then there's an extension, so the stable envelope, step plus. So this is again, so this is an open set here, this is an open set here, and its elliptic homology is kind of the opposite, would be an inclusion of a closed set. And so then the question of extend sections here to sections there. And then similarly here would be kind of step minus. And the analog of the R matrix is the ratio. Monodrome is step minus inverse composite step plus. So no. This is again should be very familiar to Constantine, because this is how you construct, you know, kind of various derived equivalences you know, in the world somehow. This should be the trace and K theory of some derived equivalences for like loops into X. But you know, let's not talk about that. But that's you first extend to the stack and then you restrict to the other thing. That makes sense? You have a class, you extend it. You have a class on the stable logs, you extend it to the stack, and you restrict it to the other stable logs. Yeah. Well. Anyway. Yeah. That's a. All right. Yes, we should all praise Dan. Your student Dan is great, and Dan is. I was great to have Dan at Columbia, and well, I don't know. So this is entirely parallel. I mean, that is not entirely parallel. Should be really. This is already says in our. I mean, there's a discussion of that in our work with Mina, and we already say there that that should be the action on K theory of some derived equivalences for loops into X. So that work hasn't been. You know, you can watch. You can. There's some discussion of that, and nothing written, but there's some talks on the. I mean, there's some passages in our text but there's some talks on the web you can listen to. But that's so anyway. That's thing number one. And now already in that paper with for where G is for G equals product of GLN VI, and X is some kind of quiver data. So this is kind of Nakajima variety context. This map, this is computed in our paper. So this is the paper we called like quasi map count and beta eigenfunctions. So this is in this beta paper. I'll write beta since. So we wrote more than one paper with me, and there's in particular for this particular map, there's in the case when you have the fact that X is quiver is not so important, but the fact that X is a product of GLV, there's some separate trick that reduces in here, reduces to the old problem, reduces to in fact to the group, to the kind of C star stable envelopes. There's some trick there, but there's some auxiliary stuff, and you know, it's a nice trick. So you can write, but in general, this extension here, I think, the way I can prove it, today is by this sort of inductive argument, exactly paralleling. So you take the unstable locus, you filter it by various Hardy-Nernst-Simons strata, you induct strata by strata. The strata may have the homology vanishing, so that's how you extend it. That's how you extend the class. So okay, so now another application. It's to this 3D mirror partners. Does I have X?
So, sorry, just but
Yeah.
in your new setting, you can compute such monodromy problems for things like generic Coulomb branches, like slices in
Coulomb.
F1 for example, right? You don't have to work.
Coulomb, I'm
not the vertex
sure,
function,
so.
but the monodromy, but it's monodromy. You can understand for things like, is that correct?
No, I think this is still kind of a Higgs branch computation. This meaning I still
No, the vertex function, of course, but the stable envelopes themselves.
Oh yeah, the stable
now
envelopes.
you can
I think the stable, exactly. Yeah, I think the stable envelopes you can define, you know, whatever. Whenever you have the. So in other words, you don't need. So right in your construction we needed the presentation of a variety as a quotient of something nice by something nice to have.
Well, because we wanted the solutions as well. We didn't just want the monodromy. But if you're just interested in monodromies, you can. I see.
So this maybe I'll emphasize this. So this in the previous work, maybe I'll somehow restate what I said before. The previous work on the elliptic stable envelopes is their construction is given by global arguments, and the global arguments use the fact that we take a quotient of an I space by an S space, and so in particular, I was amenable to variety that can be presented in a particular way. So it's not. Not the very general, not the most general algebraic variety. And so this is one thing, and also, which is in a way it's nice because it gives you a formula. It's a global thing. It gives you a formula. Like for example, for the Hilbert scheme of points, you can read this formula in Andrei Smirnov's paper, and that's it's not maybe it's not the simplest formula. It's a formula. So it's a formula which you can use. But whereas here you get an inductive construction, which is it's not a formula. It's not, you know, you want to know at the end what this thing is, you have to either go through this inductive construction or be somehow smart in some other way. So this is also for this particular problem, when you take this is we first studied this problem for like an abelian group action on some nice quotient, and that problem we solved. But here we're talking about a non-abelian group action, but we invented then a trick that reduces on some auxiliary space, reduces this this stable envelope for non-abelian groups to abelian groups. In fact, to C star. There was just some nice trick, some nice auxiliary space, and again it gives you a formula. But this type of argument will not give you formulas, but will prove that the monodrome is monodrome is what it is. So it's not. And so now again, 3D mirror partners is another thing that where we wish we had a formula, but we don't have a formula. And so again, so this is again some me and I. We have this provisional definition. So provisional, or maybe what do you call it? It's like maybe sufficient condition. It's not definition, maybe sufficient condition. Condition is the following: you have a torus action on both sides. So maybe here's a torus act, some torus A here, and has this fixed point, this isolated fixed point, and then there's some torus A check acting there, such that if I take the fixed locus, so maybe X A, some fixed locus, PI, that is some bijection, maybe call it PI with the X check, A check. And sufficient condition is the following, that if we take the vertex functions for this PI, so to write down a vertex function requires to present the space as a quotient. So this means this is a point, but it's really presented as a non-trivial quotient. So this means this X in this world, X is a quotient. It's some quotient, something by something of maybe LCI bireductive, something like this. In fact, maybe smooth bireductive, or something. So and so this means to talk about vertex function, we need representation of a variety as a quotient. Otherwise, because we want to talk about this quasi-maps, they use the fact that something is a quotient. And so this PI, since being a fixed point, is inherent this quotient presentation. So this is not trivial thing. And that thing, so this is now a function. Since it's a point, has no action here, and so this is depends only on this variable z, zi, that's it in that torus z, and maybe another variable called h bar, which is the weight of the symplectic form. And what we would like this vertex function to be up to some, whatever, roughly, to some conventions. Maybe I'll write since we're 1 minute before the expiration of the talk, maybe write approximately up to conventions. What we would like it to be the vertex function for you take the tangent space at the point PI check, and that is just a vector space as a vector space.
Sorry, Andrei, this is a condition for what? For the mirror or?
This is, so in general, there should be some definition of a mirror involves comparison of vertex functions, for example. And this says that if this is the case, then it's a theorem that in fact they're mirror in the sense their vertex functions are equal. With the change of, so it's a vector space with an action. So this is with an action. With an action. Of this A check, which one identifies with that. And kind of H bar prime, which one identifies with something like Q over H bar, something like that.
I see. Only checked it in type A, or you think it's true for any kind of?
No, I think it's not a true statement. It just says if this is the case, then the things then it's a theorem that the guys are mirror, meaning their vertex function are the same. And the way you can have different definitions of a mirror, but one definition you can say, well, if the vertex function are the same with the exchange of variables, means you trade what was equivalent variable into Kähler variable and vice versa, and then the H bar there's some substitution, which I think is this, but one has to look in the paper too.
But it doesn't tell you how explicitly the K-theory class is mapped, right? On the left and on the right, it's some complicated map, right?
And say it again.
So you have, in principle, you can ask if you can find the map between K-theory classes for X and for
right,
X.
but I mean, there's better. What one would like to have one, so part of that construction. So this is part of that construction was this construction of this mother class, or this duality interface. Which is an elliptic homology class.
But even before the mother function, right? One.
Mm-hmm.
I thought one wanted to say that somehow the vertex function of a specific fixed point of X is like the vertex function of X check, but in the stable basis, like
something like that, yeah.
Right. Is this your squiggle? Maybe I don't understand what your squiggle means, but I mean,
no,
basically some conditional Neumann boundary condition exchange, which is what mirror symmetry is supposed to do. And this was right.
Right, but in particular, the way I defined the vertex function, I think something with my video. Oh, okay, maybe it's working.
Yeah, I can't see what you defined.
So what I defined as vertex function didn't have, for example, this perturbative contributions, which you have to put. But I mean, they didn't have that prefactors that we want. So this means up to some stuff which I haven't defined. So. But
you would map a fixed point on X to a specific K-theory class on, or
that's right.
Specific elliptical
right.
homology class, namely the
exactly.
stable basis class. Good. Okay.
So what we would like is to have a. So if I have a kind of maybe I draw X. And then X check, and then there are fixed points. P1, P2, and then P like this P1, P2, P1 check, P2 check, check. What we would like is we would like to have a map which sits on the union of attracting manifolds of these guys. Which class? And something like that. This is the union. This is the union of attracting manifolds of PI check. Something like that. And has the property that if I restrict it to if I restrict it to a fixed point in one copy, so if I restrict to this, so restriction to this is the restriction to P I check. This equals the stable levels for X. Just write step. That makes sense? Up to whatever, some stuff. And so now, again, we would like to have an explicit formula. So there is an explicit formula. There is an explicit formula for hypertoric. But hard in general. And so, in general, in the absence of explicit formula, one can proceed again by induction. By induction, in fact, the way one inducts is that the poles is, somehow this sort of since we already have, the z and this variable h. Here were the pole. I mean, this is where this has to do that. Remember at some points these were the variables on which the stable envelope depended. So these were the poles that we didn't know what they are, and now these are the same. This we know that these are the same as maybe up to some correspond here. These poles correspond to the weights of a check, bar check, in the tangent spaces to X check, right? And so they become, these poles, they become objects of exactly the same kind. Remember when we had so maybe to somehow try to well, I'm now spoken for 2 hours, so I have to wrap this up. But you imagine you already defined your class maybe here and there. So sorry, maybe different color. Suppose it's already defined like here and like there, and you now want to extend it here. So today I'm getting I apologize, computer's tired, so you must be very tired. So now I already have the class defined on the blue part, and I want to extend it to the red part. And then this means and then this would be saying what? So that I can extend the class. So if I argue kind of like if I argue horizontally, like if I argue, let's say I argue horizontally, I argue for X, or sorry, vertically, I argue for X. For X, I have my class, I can extend it, except I have certain poles I have to worry about. There's some H1 I have to worry about in this space of parameters. But since I already have my class extended here, I already have taken care of that since if you think the role of having already class defined in this blue part, it exactly says that it's okay. The poles are under control. I'm not going to get. So in other words, what does it mean the poles? It means I have some co-kernel of a map that goes to H1, some abstraction to extension, and as abstraction to extension, this really says, well, in this language it says I need to have my class already extended in this blue part, but that extension I have. So that's the kind of that's the kind of induction you can run, and And again, this will give you this interface class like without an explicit formula. Maybe one would like to know, because the knowing the formula for this class is to know how to pair the two how to exactly pair two theories. But one would like an actual interface, a pair. So the whole there's a long discussion. Maybe you can like about a year ago, me and I, well, I was speaking in Uppsala, but anyway, talk on a joint paper, and so that you can watch that. So there's long discussion of what does it mean to have an interface like that. And with this sort of argument, you can prove its existence without giving an explicit formula for it. And that's well, sorry, I was hoping to use under 2 hours, but it's exactly 2 hours now. Maybe I'll stop now.
Okay, Andrei, thank you. We won't do it jointly because it just creates a lot of noise, but thank you for the wonderful lectures. Let's see, do we have, we should probably let Andrei go because Ina's waiting, but do we have other questions?
Can I make a comment?
Sure.
Yes, about the last part. So like, so you said that you have explicit formula for hypertoric, but so we also have formula with titling for type A. It is slightly different approach. So we know how explicitly map K-theory classes from between X and X check, and that uses the fact that the vortex function is satisfied by some Q hypergeometric equation. So we have a dictionary of how to map classes here and there. So like, we think it should work for other types, but yeah, so far we have formula for explicit formula for type A. Yeah, so basically you have some K-theory classes for X, K-theory classes for X check, and yeah, there is some combinatorial construction. So which uses the dual interval system. Yeah.
No, I'm sure there are many cases in which formulas can be given, but I also think that if you want to write the case for the actual formula for the Hilbert scheme of points, it's probably going to be pretty complicated.
We're writing a paper right now about that. So to this, you need to take an infinite quiver, and then you need to impose some periodic conditions. So we already know how to do it for the, so how to understand this integral system for A infinity quiver. So you have A infinity quiver, and then you just need to close it up in a loop, and it works like that.
David, do you have a question?
Yeah, just one. I mean, it's not a question somehow. Why elliptic cohomology? What is the?
So that's right. So this is maybe a short answer to that. I spent some time in the first part that said, talking about how all that stuff is supposed to be an interface, and like an interface where an interface in 2 + 1 dimensional field theory. In a 2 + 1 dimensional field theory, what's the boundaries that will look like? Well, it's some boundary along the Riemann surface, the space of the theory. So it's one thing, and then there's time, and so here's your torus, and that's why you need elliptic homology. Yeah, I mean, somehow this is the I'm not, since times immemorial, people were talking about like the that the K theory has to do with like maps of loops to your, it's like the cohomology of the maps of loops, and then elliptic cohomology is like the cohomology of maps from a torus to some whatever. And so here's since you have some degrees of freedom that live on a torus, and you'd like to associate something to that, the place for that is elliptic homology. That makes, maybe Mina can say more coherently, but
I mean, also elliptic integrable systems, we need some geometric background for those, right? And that's what this elliptic homology is doing in a sense.
No, I don't think this is. Yeah, unfortunately, there are no elliptic integrable systems. So
why? I mean, there are elliptic integrable systems. We know them, right?
Because in the elliptic integrable system, they only can happen in like the weight zero subspace of your representation, and most interesting representation don't have a weight zero subspace. So we, put it differently, elliptic gauge integrable system probably have to do with like four-dimensional gauge theory, but there are not so many gauge theory that make sense in 4 dimensions.
I mean,
Like if you want to write an elliptic, if you want to write an elliptic analog of your QKZ or something like this, then it only makes sense in weight zero representation. Weight zero of your representation.
I understand.
And most things we talk about here, the corresponding representation has no weight zero subspace, or it's somehow trivial. So
also, there's double elliptic systems when you live on some abelian surface, like it's more complicated.
I don't know. Maybe something like, yeah, maybe there's something, but it has to do. Well, anyway, maybe this is kind of perpendicular to the discussion I wanted to talk here. So this is more in terms of classical integrable system. This is a question you take some integrable system associated to quantum loop groups such as QKZ or something like that, and you compute it either the eigenfunction or monodrome or integral representation for solutions. All of that you do in terms of elliptic homology or its degenerations. But this is somehow to compute occasionally you can also write some elliptic difference equation, but those, to the best of my knowledge, they only make sense in very limited generality. But then I'm prepared to be corrected. I'm not studying them here anyway. So.
Yeah. So this is. I mean, I'm not adding anything. This is just a particularly rich setting to study this problem because of three-dimensional mirror symmetry, and the theory basically uses up all the richness of physics that there's there. So the existence of Kähler and equivariant variables and mirror symmetry are exchanging them and so forth. I have just a brief question in that from way back when we were writing the paper, I recall that from physics perspective, understanding what is elliptic stable envelopes are for sort of everything that was massive was easy in that you could sort of understand it just geometrically. But then if the hard part was understanding the contribution of massless matter. So in the language of the picture that you drew, this will be analogous to the hard part is precisely understanding the blue boxes. Once you know those, everything else kind of follows. But this new approach it must improve on this somehow. In that, for example, in the setting where I wouldn't be able to do very much at all is the case if you just have if you don't have isolated fixed points, say, but there's a whole families of those. So there's lots of massless matter fields. Then it was very hard to sort of say what this is, and it requires a lot of hard work, some of which, for the Hilbert scheme of points was done by Smirnov. But so does your new approach improve on that direction? Just kind of headache?
No, I don't think
it improves.
Yeah, I don't think as long as your question has to do with explicit understanding of anything, I don't think this helps you in any way. I think it's.
But the way your recursion works is once I understand the blue boxes, I can expand out, right?
Yeah.
Sort of that's okay. Thank you.
But this is the way it's done. It's like saying, there's some, roughly speaking, it's like solving an interpolation at every step, and you know that interpolation problem has a solution, but it's, I mean, so how you can, I'm not offering you any kind of formula for solution of that interpolation problem.
Okay, do we have more questions? Questions?
Can I ask notational questions from way back? Sorry.
Sure.
So when you introduced xi, that implied that there is a total ordering, right? On the
No, partial enough, but you can extend it to a total, yeah.
okay. Is there a reason why it always?
Yes, because if I have a like a torus action on a projective algebraic variety, then there is an attracting order between the all the fixed components.
Okay.
What's attracts to everything? Somehow that's the order, yeah.
Okay.
Or quasi-projective algebraic variety. That's enough. Or
So I could ask a question if there's nobody else. You draw a parallel. I didn't quite understand if it was a statement or just a parallel between the quantum K-theory and the elliptic homology class. Now, while we do think that K-theory, elliptic homology or so is always an extra loop involved, we don't think in topology that we're seeing instantons like holomorphic maps. But you are drawing a parallel between quantum K-theory, which sees instantons, and elliptic homology, which, unless you make it quantum, doesn't. So I'm trying to understand why there should be a connection there.
Well, I think the sorry, maybe I'll answer not not your question, but some related
Different
question. But yeah, but the kind of thing I have in mind is that this evaluation map. So if you have this quasi map from P1, I want to know what it does to at the neighborhood of some point. You can take evaluation map for quasi maps from formal partial disk. So there's some I have a quasi map from some some kind of curve that has a point. Then I can take, then there's an evaluation map to the following thing. So you take like a quasi maps from the spec of C X inverse X into your variety X, something like that, right? And moreover, not only you go there, you go to a universal cover of that because it not only tells you what the loop is, but also tells you how to trivialize a loop. So you go to a universal cover of that space. Right. So you should really push forward K-theory classes from here to K-theory classes here, and then you should really study those. But and this is the various elliptic homology classes we discussing. They really kind of stand-ins for suitably equivariant. The fact that I want to have all the scalar variables around is that because I'd like to have equivariance with respect to deck transformation and so on and so forth. So that's not something funny happening with the internet. You guys seeing a funny picture of me or? No, I'm receiving a pretty funny picture of myself.
We see some.
It's frozen.
Snapshots, yeah.
Yeah. But okay, so that would be. And in principle, one should just go ahead and whatever. Instead of working with the K-theory of that space, you take the whole takes a suitable category of coherent sheaves on it, but that would be, but it's, that sounds like a project, and it's not something one can do over like before lunch. So it sounds like some stuff. It'd be good to develop it. I'm hoping someone will do it. So that's what
is this? What is the status of this So you're making this space that you've written, this quasi-maps from the punctured disk.
Yeah. So that space is certainly, it's totally fine because, I mean, that space exists.
And is it a true fact that K-theory of that is elliptic cohomology, or is it conjecture, or is it a definition?
It's,
What's the...
That I don't know. I mean, there are many people who, I mean, actually, you can ask, maybe Konstantin knows better than I, but there are many people who somehow prove theorems which sound something like that, but I didn't prepare somehow to give you for giving any sort of summary on that topic. So
but it's not like infinitely far away from the current state.
It's not infinitely far away. Yeah, it's in the general ballpark. Yeah.
Okay, any more questions? Okay, if there are no more questions, maybe we should let Andrei go and thank him once more for the 2 great lectures, and and thank you for joining us on your anniversary. I guess we should thank Ina rather.
Yeah. I'm really touched you guys somehow. You know, it's a very technical subject. I really deeply touched you. Listen to 4 hours of this stuff, and it's kind of so.
Well, I think the way this goes is 4 hours is sort of the minimum to actually start understanding something.
All right. Thanks so much.
All right. Thank you. Thank you all for joining. Okay. Bye, everyone.